Okay, so we're going to work through the practice question on page 41 here, just to look at how we're going to calculate all these different values, how we're going to calculate delta G, or calculate a temperature if we know the delta G. So first, we can make a prediction about the sign, negative or positive, of the entropy change for this reaction, explaining our reasoning. Well, on the left, the first thing I look for is states of matter. And I see that on the left, I have 3 moles of gas, which is the most disordered, highest entropy state. And on the right, I have 1 mole of liquid. So to me, I can right away say that this is going to be a negative delta S. We're going to much more order. It's a big decrease in entropy. And my reasoning would simply be what I wrote up here. 3 moles of gas are becoming 1 mole of liquid. So we're not only going to way fewer particles, but also particles that are closer together and more orderly than they are in the gas phase. So fewer moles and liquid more ordered than gas. But actually pointing out numbers like 3 moles of gas to 1 mole of liquid is things that you'll often see on the mark scheme. Okay, first, using table 12, calculate the enthalpy change for this reaction. So in terms of enthalpy change, if we look to table 12, this is going to be with enthalpy of formation values, and we can calculate the delta H of a reaction by adding up the formation values of the products and the formation values of the reactants. And delta H formations of elements in their normal state, in their standard state, are equal to 0. So that means that hydrogen, which is an element, won't have a delta H value. So on the left here, I've got carbon monoxide, and on the right here, I've got methanol. So if we go back to table 12, which is here, then we should be able to find carbon monoxide, and we should be able to find methanol. And we're going to have to use a couple of values in this question. So notice that the delta H formation values are here, and the delta S, or just the S values, which I'll use in the next part of the question, are here. So that's where I'm getting my values. Now, if you're watching this video as you're trying this question, I ask you to please pause the video now and try to do the calculation first, and then watch my solution afterwards. Okay, so let's assume that you have paused the video and tried it. Now I'm going to plug in that the enthalpy of formation for methanol, the product, was negative 239 kilojoules per mole. And the delta H for the reactant, carbon monoxide, was negative 110.5. And again, I get to ignore hydrogen because it's an element. And overall, that means the enthalpy change is negative 128.5 kilojoules per mole. So this is an exothermic reaction, which means the enthalpy term is favorable in terms of spontaneity. Now, if I go down and now I want to calculate the overall entropy change, the delta S, same idea, very similar. We're going to add up the S values of the product and subtract the S values of the reactants. Now, the nice thing here is that I already have kind of a guide. I know that I should have a negative entropy change. I already thought about what's happening with the particles and the change of state. So when I'm done, I'm going to have a good double check on if I've done the math right. So when I do the values here, I have 127 is my value for methanol. And then I need to add up the values for the reactants. So I've got 197.7 for carbon monoxide. That was from table 12. And then hydrogen's value, you'll notice that it's given here. The elements aren't listed in table 12 because they don't have those formation values. So if there is an element in your question, it'll have to be given to you in that question itself. Now, in the equation, there are 2 hydrogens, 2 moles of hydrogen, and these values are always given per mole. So that means I've got to do the 197.7 and then 2 times 130.5, which is the value for hydrogen. So overall, I get 458.7 for my reactants, and I have my 127 for my products. And when I subtract those, I get a delta S that indeed is negative 331.7. And that's my delta S term. And so that's good. I got a negative value, which is what I was expecting. Okay, determine whether or not the synthesis of methanol is spontaneous at 25 degrees Celsius. So any question about spontaneous is a question about delta G. So they want us to calculate delta G. And if it's negative, then we say, yeah, it's spontaneous. And if it's positive, then we say, no, it's not spontaneous. So delta G is delta H minus T delta S. Okay, so I just plug in my values now. It's pretty straightforward. I have minus 128.5 for my delta H term. I've got 298 in kelvins. I've converted 25 degrees Celsius to Kelvin. And I've got my delta S term. And what I'm going to do here is right away, I'm going to move that decimal place over 3 spots and make it 3 places, factors of 10 smaller to make sure it's in kilojoules. And when I do this part out, I get a delta G at negative 29.7. And this is in kilojoules per mole. So it is spontaneous. It's considered a spontaneous or favorable reaction at this temperature. And if I had to give a reason why, because delta G is negative. If delta G is negative, that is sort of the definition quantitative value to support whether or not something is spontaneous. Now this one, the last question is determine the temperature in Kelvin at which the reaction becomes spontaneous or changes from being spontaneous to non-spontaneous. And if you get that question, you set delta G equal to 0 and you plug in your values and you solve for T. Because this T value that we get is where 0 is where you flip from being positive to negative or negative to positive. So I've plugged in my values, once again, the S value being divided by 1,000. And now I'm going to solve for T. So it's a little straightforward algebra. And in the end, I get T is equal to 387.4 Kelvin. And they didn't ask me to, but why not? That's about 114 degrees Celsius. And so if we think about it, if we go above that temperature, they didn't ask for this, but why not? Above 114 Celsius will be non-spontaneous because the entropy factor is not favorable. It's negative entropy change. And so if the temperature gets too big, too high, then we're very unlikely to do a process where we have to create more order. We're going from gas to liquid. If it gets too hot, that process is not going to be spontaneous. And so that's why above 114, this reaction will no longer take place spontaneously. If we are below 114, then this ends up being an energetically favorable and spontaneous process. And that's because the enthalpy change is quite exothermic. And so overall, even though it becomes more ordered, we would consider this an overall spontaneous process so long as the temperature is below 114. But this would be the solution to the calculation part of the question. And so that's how you can use this equation to solve for all these different values. Table 12 to use to get delta H, to get delta S. Then you can use that equation to get delta G. And you can use delta G set equal to 0 to solve for temperatures at which reactions change from spontaneous and non-spontaneous.